In this video, we are going to do a little bit of practice with the properties of a relation being reflexive, symmetric, and transitive. So we're going to talk a little bit about equivalence relations. And we're also going to learn how to use Mathematica to help us with these aspects of relations. So the first thing I'm going to do is open up Mathematica. On my computer, I'm going to go to my Start menu, and I'm going to open it up. It's right here in my panel. On the school computers, there should be just a desktop icon that has this kind of funny shape, and it should say Mathematica right underneath it, and we're going to click on it to run it. So it starts up, and the first thing you want to do is open up a new document, and Mathematica opens for you. So I'll make mine full screen here. Now this is something a little bit silly, but sometimes Mathematica can take a little while to initialize. So what I always do when I first open up Mathematica is I type in something easy for it to do just to warm up. So I almost always ask Mathematica to tell me what 1 plus 1 is. And in Mathematica, if I hit enter, notice that nothing happens. It just moves the cursor to the next line. That will always happen with Mathematica. Mathematica uses enter to just give you more space to enter in what you want. So if you want to tell Mathematica to compute something, what you actually have to do is go up here and hit shift, hold shift while you hit enter. And then Mathematica says, oh, you really want me to compute something, you don't just need more space, and it gives you the answer, output of 2. So it did that very quickly. So Mathematica is up and warm and ready for us to use. So what I'd like to put into Mathematica today is I'd like to take a look at this, one of the relations that we studied in our worksheet. We were looking at the set A, which was the set of numbers 3, 4, 7, 9, and 14. And we were going through that set of numbers. Here, let me put it on the screen just so we have it. So A, that's the thing that I want to define. When I'm defining something in Mathematica, instead of using an equals, I use a colon equals. That says I want to create something. I'm going to call it A, and I want to define it to be the following. So what do I want to define it to be? I want to define it to be a set. So I use my squiggly brackets for set notation. It's a set of numbers 3, 4, 7, 9, whoops, and 14. And that's what I want the set A to be. And when I'm done defining it, I could just go ahead and hit Shift Enter and everything would be fine. Or I could put a semicolon after it, which means when I'm defining something, there's really no need for an output. If I just hit Enter, Mathematica will spit out what I just put in for me, and it'll say, yes, A is 3, 4, 7, 9, 14. So if I want to say, Mathematica, you don't need to bother telling me that all over again. I know what A is equal to. I told you what A is equal to. I can put this semicolon at the end of it, and that will suppress an output. So now I hit Shift Enter, and it just shows me an input with no output, but it's ready for me. It's showing me these lines right here and giving me a new cursor saying, okay, got it. I'm ready to move on to the next thing. So here's my set A, the set of numbers 3, 4, 7, 9, and 14. And what I wanted to do is create a relation from A to A where two elements of the set A are related if they have the same remainder when I divide by 5. So what I mean by this remainder is I'm going to go ahead and I'm going to take a number like 14 and I want to break it up into 5 groups. And I want to put an equal number of things into each one of the 5 groups as much as I can, and there may be some left over. And whatever that leftover is called the remainder. So for an example like 14, if I were going to make 5 piles, and I have 14 things to try and put into 5 piles with the same amount in each pile, I can put 2 into each pile, but I can't put any more. I don't have enough to put 3 into each pile. So if I want all the piles to have the same size, there will be 2 in each pile, but more importantly, there will be 4 things left over after I've done that process. So a number like 14, that's going to have a remainder of 4 when I divide it by 5. And so 4 and 14 in particular would be related. Now here's what I want to do. I want to go ahead and make a 0, 1 matrix going through all these numbers that represents the relation I want. So let's use R for relation. Let's define our relation, and let's define it as a matrix. So R is defined to equal, and I want it to be equal to a matrix. Now, in Mathematica, if you're quite good with Mathematica and you're used to its nomenclature, you can do a matrix as a list of lists. But that's a little bit difficult, and if you're just starting out with Mathematica, that maybe isn't very intuitive to you. So maybe what you want to do is actually make this relation look like a matrix. And Mathematica will allow you to do that. If you're less familiar, it will put things in a nice format where you know what's going on. So let's go up to Insert and go down here to the option of Matrix. And we want to make a new matrix, and then a little screen will pop up asking us what we want the matrix to look like. So I want to make a new matrix, right, list of lists, and I wanted to have, there are 5 things in my list, so I need 1 row for each entry of my list, and I need 1 column for each entry of my list, and I don't want it to fill with anything. I just want it to be blank. And if I wanted to draw a frame, make it look really pretty, we can do that. Right now we just won't do anything. I hit OK, and here's what it does. It takes R and it gives me this 5 by 5 grid right there with all these little boxes that are empty. And what I need to do now is I need to go back up here and click on each of the boxes, and I need to fill that in with a number. So this box right here that's highlighted, that represents 3, as I'm going to go in sort of numeric order, increasing order for the rows and the columns. So this box right here represents 3, 3. Is 3 related to 3? Does 3, the row, have the same remainder when divided by 5 as 3? And yes, it does. They have the same remainder. That remainder is 3. So because the answer is yes, we put a 1 there. Then we move on. So I'm thinking of 3 as the row, and now I've moved on to 4 as the column, and I'm saying 3 and 4. Did they have the same remainder when I divide by 5? One of them has a remainder of 3, and one of them has a remainder of 4, so the answer is no. So put a 0 there. Moving on, 3, still looking at 3 for the row, and now 7 for the column. Do 3 and 7 have the same remainder when I divide by 5? The remainder of 7 when I divide by 5 is 2. I can put 1 thing into each pile, and then there are 2 things left over. 3 and 2 are not the same, so no. 3 and 7 are not related. Moving on, 3 and 9. 9 has a remainder of 4 when I divide by 5, so 3 and 9 are not related. And similarly, 14 has a remainder of 4, not 3, so these 2 things are not related. And now let's go on. Now we're moving on. Let's do the 4 column, and then I'll just sort of fill in the rest automatically. Presumably you've done this exercise, so I'm just reviewing. Here, this is the 4, 3 entry. So I'm saying, does 4 have the same remainder for the row as 3, the column, when divided by 5? And the answer is no. But 4 does have the same remainder as 4 when I divide by 5, so I'm going to put a 1 here. Also, 4 and 7. 7 has a remainder of 2 when divided by 5. 4 has a remainder of 4 when divided by 5. So those 2 things are not the same, so 4 and 7 are not related. However, as we said before, 9, if I want to break 9 up, I can put 1 thing into each pile. So 5 piles, 1 thing goes into each pile. That uses up 5 of my 9. And then there are 4 things left over. So the remainder of 9 when I divide by 5 is 4. And that is the same as 4. So 4 and 9 are related. So put a 1 here. And similarly, 14 has a remainder of 4 when I divide it by 5. So 4 and 14 are also related. Now the rest I'm going to fill in sort of automatically. I'm going to go kind of quickly. So this would be 7, 3, 7 and 4, not related. 7 is related to itself. And then 7 is not related to 9 or 14. Oops. And this is now the 9 entry, so 9 is not related to 3. 9 is related to 4. They both have a remainder of 4. 9 is not related to 7. 9 is related to itself, and it is related to 14. 14 and 3 are not related. 14 and 4 are related. 14 and 7 are not related. 14 and 9 are related, and 14 in itself are related. So this is my relation that represents what we wanted. If 2 numbers in this list have the same remainder when divided by 5, then we put a 1 there. If not, we put a 0. And this is my relation. Again, we'll suppress the output, and I hit Shift-Enter to make Mathematica know what my relation is. Now here's the thing that we wanted to discuss. This is the relation. We've talked some at this point about how we determine what the relation is, given the description of what it should be. We've got it figured out here, and we've got it represented as a 0, 1 matrix. What I'd like to ask now is this relation a reflexive relation? That is, do I always have, for each element of my set A, do I have the ordered pair, little a comma little a, in my relation for all of the different elements in my list. And I see very quickly from this 0, 1 matrix that the answer to that is yes. Every number does have the same remainder as itself when it divided by 5. And the way that I could pick that up really easily from my matrix is I could notice that I have all 1s along this main diagonal here. That's the property that I need to check when I have a matrix to determine if it is a reflexive relation. Now, how about a symmetric relation? Whenever I have an ordered pair, little a, little b, inside my relation, I want to know if I also have the element little b, little a inside my relation. So AB, that would mean go down to row A, column B. For example, row 2, column 4, be this entry right here, this one right here. Is it always going to be the case that row 4, 1, 2, 3, 4, column 2, also belongs to my relation? It turns out that the answer is yes here. If you say it out in words and describing what the relation is, if A has the same remainder as B, does B have the same remainder as A? Yes, that seems clear to us. And so that would be one way perhaps to convince ourselves that our relation is reflexive, but a very easy way, symmetric. A very easy way for us to see if our relation is symmetric just from looking at the 0, 1 matrix of that relation is to check, again, we focus in on this main diagonal, and we look at symmetry if we reflect across this main diagonal. So in other words, one thing that we could do, and you're going to have to follow my mouse here, is we can go and look at all of these diagonal rows, this 1, 0, 0, 0, 1, 0, big row of zeros, and then 0, 1, 1, 1, 0. We can look at all these little diagonals going across here, and we can check to see if they are symmetric. Are they like a palindrome? Do they read the same forwards and backwards? In other words, if I were to take this matrix and fold it diagonally across this main diagonal, would everything match up? Are we symmetric when we fold across that line? And if so, then your relation is symmetric. And so you see by examining this particular relation that this is a symmetric relation. Now, the last thing that we need to ask is this relation transitive? And transitive is a very tricky, is the trickiest of the properties to see in any of the forms that you're looking at. Is this a transitive relation? And the good news is, with matrices, there's not an amazingly easy way to see that just from glancing at the matrix as there is with reflexive and symmetric properties, but there is a really neat trick. And what's awesome is that what's hard is that that trick involves matrix multiplication, and we're not going to spend a huge amount of time on matrix multiplication, if any, but it is a little bit of a tedious process, and it's really easy to make mistakes if you're multiplying matrices by hand. The great thing is that computers don't make mistakes unless the users input mistakes, and Mathematica can multiply matrices extremely quickly and extremely accurately. So here's the trick. Here's what I want to do. I want to take this matrix and I want to square it. I say that in conversation, but the command for Mathematica in that to multiply matrices is I want to take a matrix, R is my matrix, and I want to dot it with itself. This means R squared. Takes R and multiply it by R. And if I do that and hit Shift Enter, what I will get is the resulting matrix as if I would have taken R and multiplied it by itself, R squared. Now if I hit Shift Enter, as I just did, what you'll get is a list of lists. This is how Mathematica internally thinks about matrices. Remember, I cheated and I told it to insert a little matrix for me, and Mathematica went and put this pretty formatting in there. If I just ask Mathematica for my matrix R or for any other matrix, it will give it to me as a list of lists. And what this really means is this first, it's a list, and this first list is the first row of the matrix, and this is the second row of the matrix, and the third row of the matrix. So these lists inside of the larger list are just the lists of the rows of the matrix. But let's say we don't like that. Let's say we really wish that Mathematica would show us the matrix as a matrix in the pretty way that it showed us the last matrix. Then there's a big trick for that. We go back up here, and where we take r and multiply it by r, what we need to do is tell Mathematica that we want it to put it in this pretty matrix form. So what we do is we hit this double, forget if that's, yeah, it's forward slash, 2 forward slashes, and then we say Mathematica, we'd like to see this in matrix form. And Mathematica is nice. It sort of suggests options for you, as it did there. And so we say, yes, matrix form. Mathematica likes capitals, as you'll notice, so a lot of its commands start with capital letters. Matrix, capital M for matrix, capital F for form. Again, now I hit Shift-Enter, and watch what Mathematica does. It stacks those rows for me and makes it look like a very pretty matrix. So, I've told you what you need to do now inside Mathematica, but what's the trick for determining if this relationship is transitive or not? Here's the trick. What we want to do is we want to go entry by entry and compare these two matrices. So here's my original matrix and here's the square of my matrix. And what I want to do is I want to focus on all the places in the squared matrix where I have a non-zero entry. Any number in the world other than 0. And what I want to do is I want to compare. If I have a non-zero entry in this matrix, then I want to look at the same position in the original matrix, and I also want that to be non-zero. If I can go through the entire matrix and every time I find a non-zero entry here, the corresponding position in the original matrix is also non-zero, then the relation is a transitive relation. And if I can ever find any spot in this square of the matrix where I have a non-zero entry here, and it happens to be the case that there's a 0 entry in the similar position in my original matrix, then the relation is not transitive. So it goes both ways. First of all, if I can go through and every single place I have a non-zero entry here, there's a non-zero entry here, then the relation is transitive. And if there's ever a time where that fails, there's a non-zero entry here, and the corresponding entry in the original matrix is a 0 entry, then the relation is not transitive. If you do that process for this particular relation, you'll notice that every single space where I have a non-zero entry here, either a 1 or a 3, as it turns out for this example, I always have a 1 in the original matrix, so this relation is a transitive relation. Now, because this relation is reflexive, symmetric, and transitive, this relation is what we would call an equivalence relation on the set A. The last two things that I want to do here is I want to teach you one more little trick with Mathematica for how to actually get this digraph representation of a relation from Mathematica. Turns out Mathematica will do that for you, and it's very pretty, so that's nice. And the last thing that I want to do is I want to talk about what the equivalence classes of this relation are. So let's go ahead and let's talk about how we know what the equivalence classes are from the matrix representation. Then let's have Mathematica draw the digraph for us, and then let's figure out how we would also find these properties in the what the equivalence classes were from the digraph. So let's go through and say, let's look for the equivalence classes on A. So what we want to do is we want to start with an element of A. We want to figure out what other things are related to it. Well, there's a really easy way. Go to the corresponding row and look for all the non-zero entries in that row, and those are the things that are related to that particular element. So when I take a look at 3, I come down here and I say go to the row for 3, which is this one right here, and the only column where there is a 1 is the column 3. So 3 is related to itself and nothing else. None of the other things are in the same equivalence class as 3. Moving on to 4, we go down to this second row in the matrix. We see that 4 is related to itself. It's not related to 3, it's not related to 7, but it is related to 9 and to 14. So 3 is in an equivalence class all by itself, and the second equivalence class of this relation has the numbers 4, 9, and 14 in it. And you'll notice that those rows, the 9th row and the 14th row, look exactly the same as the second row. It wouldn't have mattered which one I picked. Last but not least, the only element of A that doesn't have an equivalence class yet is the number 7. So we go down to the row that corresponds to the number 7. We see that 7 is related to itself and nothing else. And so the equivalence classes of this relation are 3 in a class all by itself, 7 in a class all by itself, and then the numbers 4, 9, and 14 are all together in an equivalence class. So notice that equivalence classes, it doesn't matter if you have the same number of things in each equivalence class. It just matters that every element in this list has an equivalence class. And that's about it. Now let's go through and let me have you see how we can get a picture, the graphical representation of the relation R. So it turns out that the fancy word that you want, if you have a matrix, a square matrix, meaning that it has the same number of rows and columns, and you want Mathematica to draw a picture of the relation that you have, all you have to do is take the matrix, here our matrix is called R, and you have to use the special word adjacency matrix. And Mathematica tries to suggest it for you. Remember your capitals. Let me teach you something else cool about Mathematica real quick. Let's say I wanted to use this command, adjacency matrix, and I don't really know what I should do with it. Then I type in question mark, adjacency matrix, and I hit Shift Enter, and Mathematica tries to tell me what it wants. It says adjacency matrix of G gives the vertex-vertex adjacency matrix of the graph G. Say, okay, that seems really strange. Sorry, I don't want adjacency matrix, I want adjacency graph. There. Now it says here, give me a matrix, adjacency graph of a matrix, gives the graph with adjacency matrix a mate. Now let's say I find that really confusing and I'm still not sure what I should do. One thing I can do is I can click on these double arrows right here and Mathematica will pop up this very helpful browser that tries to give me some examples with some terminology, examples, details and options, backgrounds if I want to click on that, and it gives me an example of what the input would look like and the output. And it gives me other things that I might want to take a look at. So let's see. What I want to do is I want the adjacency graph of my matrix R. Now, Mathematica uses square brackets for its inputs, so it likes capital letters for its commands, and it likes square brackets for inputs of functions. So I say adjacency graph of R, and I go ahead and I hit enter, and it drew me this nice picture. Now, it doesn't label anything, which makes sense because I didn't give it a labeling for any of these things. I just had my own labeling in my head, and then I input that. And we discussed what the equivalence classes were. Here's how we'd pick them out from the picture. Here's one of the equivalence classes. This could be 3, all by itself. It's related to itself and nothing else. Here's 7. It's related to itself and nothing else. And then here must be 4, 9, and 14. They're all indistinguishable. They're all related to themselves and to one another. Right there. Now, the thing that you'll notice is that I talked about a digraph or a directed graph, which should be a graph with arrows, and Mathematica hasn't drawn me anything with arrows. It's just given me these graphs. What Mathematica is doing is because my relation happens to be symmetric, instead of drawing 2 edges between each pair of vertices that have arrows going both directions, it's collapsed those into just one undirected edge. But if we wanted to make it draw in the arrows for us, there's a way around that. And that's to tell Mathematica that we explicitly want a directed graph. So what's the command for that? Let's see if Mathematica knows directed graph. I start typing that in, and in fact it does. It has a command, directed graph. Let's see what that command does. It says, okay, give me a graph G, and say I want a directed graph of that graph. And it will take an undirected graph, which is what we have, nothing with arrows, and it will draw the arrows in for us instead. So what we need to do in order to use the directed graph is we don't need to pass it a matrix as its input, as we did with adjacency graph. We need to pass it a graph. So if we want to take our graph that we have, the adjacency graph, and turn it into a directed graph, we have to enter a sort of funny notation. We have to say, I would like the directed graph of what graph? Well, the adjacency graph for my matrix. And when I do that, now it's drawn everything in with all the directed arrows. Notice that that didn't really change except for we added a little arrow tip on each of these individual guys, and then in these components we've taken what was one edge and turned it into two directed arrows. And that's it for this video. That's our introduction to equivalence relations and the reflexive, symmetric, and transitive properties, and also our brief introduction to doing these things inside Mathematica.